Yeah. Okay, so we were talking about fluid boundary conditions, and we got to the point of talking about something called the law of the wall, or the log law of the wall. So this is an important concept, and it does actually affect your assignment or which understanding of the boundary conditions you would use for assignment. So I'll just recap. So if we plot, if we imagine you flow coming along by a wall, well, let's imagine it's laminar flow. So you'll develop some sort of boundary layer, like a parabolic profile of the tangential velocity. Tangential velocity, I mean the velocity that's traveling along the wall, not the component coming towards. So if you were to plot that away from the wall, you might see some sort of parabolic shape. Okay. And when the Reynolds number increases, this boundary layer kind of has a universal form. So that universal form has the region of laminar flow right by the wall. So because you're so close to the wall, turbulence can't form and viscosity dominates because the velocity is going to zero near the wall. So you get a region of laminar flow right by the wall called the viscous sublayer. And then a little bit further away from the wall, not in the main flow, still in the boundary layer, still in the flow that's affected by the boundary, you have a part of the boundary layer which is dominated by inertial effects. So it's called a turbulent sublayer or inertial sublayer. And then in between, you have a buffer layer where it kind of changes between the two of those. So for everything else the same, the higher the Reynolds number, the smaller this layer might get. But it has the same general shape. So if we were able to normalize it with respect to a Reynolds number, it would be the same shape that we could compare between different Reynolds numbers, essentially different flow types between different fluids. So if y is the distance away from the wall, we just normalize y, so it's no units. So we can compare between different flow types, different Reynolds numbers, different viscosities, different densities. So y plus is y that's normalized, the distance that's normalized away from the wall. So what's it normalized with respect to? It's essentially normalized with respect to like the kinetic energy of the fluid or something like that. So this here represents the distance away from the wall. And then u plus or v plus here represents the tangential velocity. But once again, that varies depending on the fluid and the viscosity and the Reynolds number. So we can normalize that as well. So that represents a normalized tangential velocity and a normalized distance from the wall. So if we plot it with respect to these two normalized quantities, we find that for all normal flows, the boundary layer, turbulent boundary layer, has the same shape. So this looks a bit weird, but this is a log plot. So this is what it looks good. So we get a laminar region here, which actually follows a kind of linear law. So it's linear in not. It won't look linear on a log scale, but on a normal scale, it would be a straight line. So straight line looks like a curve line. And then you have this log region. So it's given by an exponential, and then an exponential looks like straight line on a log curve. So this is, and it would look like the curve line. So they have found this universal profile that seems to fit most turbulent flows. And so when you plot it, there's a normalized velocity, normalized distance, you get this laminar region, the buffer region, on the turbulence. So when you look at these y pluses, if you're less than 10, maybe you're in the laminar region. That's the thickness of the laminar region. If you're greater than maybe 30, what's that? 10, that'll be 20. That's about 30 there. And then you're in the turbulent part of the boundary there. And then maybe beyond 300 is like the main flow that you're outside the boundary there completely. So this is the shape of the boundary layer we might expect for all turbulent flows. So why do we care about that? This is how far we got the last day. So why do we care about that? Well, this can help us specifying boundary conditions for turbulent simulations. That's the idea. So let me explain why that does. So imagine we make our mesh, and I'm assuming the finite element or finite volume method here, but the same applies for finite element ranking mass. So imagine that we have flow along by our boundary. This could be the boundary of the car or the pipe or the whatever. And this is our first cell. So if we wanted to calculate the shear on this surface, the force going along this surface, we know that the formula for the shear stress or the wall shear stress is equal to the viscosity times this gradient. So if you plot the velocity going away from the wall, so it's 0 here and then increases. That's like the boundary there. If you take the slope of that right at the wall, that multiplied out by viscosity, that's the shear stress of the wall. That's the definition of Newtonian fluid wall. So let's look at this profile here. So imagine this profile here, imagine that's the true fluid profile, it goes to 0, and this is the profile here. So if you look at the true slope by the wall, you'll see it's this slope here. So if you multiply that slope by the viscosity, you get the shear stress. Fine. But imagine that my first cell, the coarseness of my mesh says that the full first cell center is here. So it's at this width. So the way the finite volume method will calculate that slope or approximate it is will say that the velocity of the wall is 0, velocity here is some value. So this velocity minus this velocity divided by the distance. That's an approximation of that slope. So if you compare that slope to this slope, it could underestimate the shear stress on the wall hugely, unless the first cell center is very, very close to the wall. Okay. So in a laminar flow, it might not be that hard to get it in this region, because this region is bigger. But for an turbulent road, this laminar sub-layer can be very, very thin. So you might need to have the thickness of the first cell away from the wall might need to be very small. So this is a challenge, and this law of the wall is something that we can help, that can help solve this problem. So the idea is there's different ways to solve this problem. One approach is to use something called wall functions. So the last lab for Fluent used these wall functions, and wall functions is one way to solve the assignment problem, and it might be the practical way. So the idea with wall functions is just say, okay, the first cell center is not in the laminar subregion here, it's a bit further away. So using this value minus the value of the wall is not a good way to estimate the slope. It's not a good way to estimate the wall shear stress. However, we know that the profile should follow the law of the wall, this profile that I showed you, this logarithmic profile. So it has a laminar region and a log region and a bulk region. So in a turbulent flow, we know that it should follow that law of the wall. So then if we just have the value here, we can basically fit that slope, and then from that value here, figure out what the slope would be if we just fit the profile that we expect there to be there. That's the idea. So we fit the law of the wall through the value here, and then that will give us an actual slope on the wall, which is not this minus this. It's a better approximation of the slope of the wall. So let's see, this says wall functions use the near wall cell center height, the height. So this distance here, this y distance, they convert that to a y plus, then they see where on that y plus graph they are, and then they use that to go back and determine what the slope on the wall would be. That's the idea of how wall functions work. In practice, how it's actually implemented in codes is when you calculate the shear stress on the wall, and rather than actually updating the gradient, they normally actually just change the definition of viscosity at the wall so that you get the correct shear stress. So if the shear stress is viscosity by the gradient, it's just easier to implement. They just update the gradient. So the gradient by the wrong, or the viscosity by the wrong gradient gives you the correct shear stress. But that's more just a practical implementation. So the idea is for standard wall functions, for a smooth wall, if y plus lies within this inertial subrange. If I go back to that original plot, so if you're in the turbulent region of the boundary layer, then it will update the definition of your shear stress in the wall to use this effective viscosity. So they add on this turbulent viscosity to account for the fact that this gradient would be poor. If your y plus is within the laminar region, so if your first cell center is close enough to the wall that you're in the laminar region, then that's fine. Then you don't need wall functions. Then you can just, that point will be here, then it's fine. You can just, you don't need wall functions, and you can just get a good value without using the wall functions. So this is showing what they actually do is if you're using an eddy viscosity Rands model, you already have this turbulent viscosity. That's a function of the flow, remember, it's not a material property. So that would be 0 by definition on a wall because there's no turbulence at the wall, but they basically make it non-zero such to account for the fact that the gradient is wrong, basically. And then you get the correct shear stress or a better estimate of it. So this is actually the format that they may use. So the idea of introducing wall functions is that you avoid the need to do this, essentially. I mean, the first cell center still needs to be within the turbulent boundary layer, within the inertial part of the boundary layer. So that means less than 300, a y plus of 300. And that means you can use wall functions, and the idea is you can get a reasonable prediction for the shear stress on a car or something like that. If you want to get a drag in a car using these wall functions. And a wall function is a particular type of boundary condition, basically. And this wall, when it predicts the drag or the shear stress, it's just using this log law, this law of the wall, to determine what the shear stress is. An alternative approach that doesn't use wall functions is to do this, basically just to have the mesh fine enough in the y direction so that the y plus, the normalized y distance, first cell center is within the laminar region. That's the idea. So if your y plus is of the order of 1, then that means the first cell center is very close to the walls in the laminar region, and then the prediction of the wall shear stress would be good without wall functions. And in fact, rather than be without wall functions, actually if you use a wall function when the y plus is small, it'll give you worse predictions. So you actually shouldn't use wall functions if your mesh is sufficiently refined, because the wall functions normal implementation will assume that you're in the log region, you're in the turbulent region. So essentially, I think it out on the slide, your your y plus should be between, I think is it 30 and 300 to be using wall functions to get reasonable predictions. And if it's less than 10, you're in the laminar region and you don't need wall functions. And if you're between 10 and 30, then the predictions are going to be poor, whatever you do. So don't have the mesh that size. It's kind of your half in the turbulent region, so the log won't work. You're half in the laminar region, and that won't be accurate. So I'm saying for standard wall functions, so in softwares like Fluid, they'll have better wall functions that try to do smarter things because users are not as smart as the people who design the software, they will claim. So if you use, there's things like enhanced wall functions, and if you look up the documentation, it's basically if your y plus is not appropriate in some places, they will automatically turn it off or turn it on or blend it and things like this. But if you are resolving very close to the wall, then the turbulence model you're using, and we talked about K epsilon, the turbulence model has to be well suited to that. So the turbulence model has to be able to predict the turbulence right up close to the wall. So the laminar region has no turbulence, but coming up to that. So if you just use normal K epsilon, it will probably predict turbulence in that laminar region when it shouldn't, because it wasn't designed for that. It's designed actually to work only with fully turbulent flows. So you'll come across something in literature which is a little bit confusing, but there's something called low Reynolds number turbulence models. And low Reynolds number turbulence models are not turbulence models for macroscopic low Reynolds numbers. In fact, it's probably the opposite. Low Reynolds number turbulence means a turbulence model that works very close to the wall. So when you get very close to the wall, the local Reynolds number becomes small, as in the velocity starts to get smaller. And there are models out there that are designed to be low Reynolds number turbulence models, as in they work well if you're resolving boundary layers. By resolving, I mean using the very much. So if you're using a fine enough mesh to get your y plus of the order of 1, then don't use wall functions, but also you have to be careful that the chosen turbulence model is designed to do that. So if you're using K epsilon, just the standard one, the standard wall functions, you actually probably shouldn't resolve close enough to the wall. The answers will actually get worse. So this is a summary. I actually have ChatGPT help me to summarize some of the differences. So essentially, this low y plus for wall resolved, and resolved normally means that the mesh is fine enough to capture some physics. So wall resolved models, in those cases, you want to have your y plus around the order of 1 or smaller, and then your first cell is in the viscous sublayer in the laminar region, and then you should not use wall functions. And for example, this K omega SSD, this is the default in Fluid and OpenFOAM, actually will work well in those situations. And for moderate y plus of the order of 30 to 300, that's the standard wall function approach. So that's when wall functions will work. So standard K epsilon with wall functions will work. And then just a comment on, for most of whatever you're trying to calculate the drag on, try not have the Y plus in the buffer region, because then you're not resolving the boundary layer and you're not properly modeling it with a wall function. And so you might ask me, this sounds like a real pain. How do I know in advance what the Y plus will be? You can estimate it based on experience, but typically what you'll do is you will set up your simulation with a best guess, run it, get the velocity field, and then in Fluent and OpenFOAM, you can look at a Y plus field. And on the boundary, you look at the Y plus field after solving it. And then based on that, you will check what the values are. And if most of the car is like 10,000, and it's like, okay, we're nowhere near even the boundary layer at all, the turbulent boundary layer. Then you resolve it. If all the Y pluses are 1 to -6, it's like, okay, we've way too many cells. We're over resolving it. And so it's by the nature of it, you'll have to iterate. But imagine you go into a company that designs cars, they'll have experience running these. They will know that for traveling on motorway speeds, the first cell needs to be a millimeter thick or something like that. So they'll already know a rule of thumb and they'll just verify that's appropriate afterwards. To comment on the wall function as well, they're designed assuming this profile, this universal profile. That universal profile is only visible on like a nice turbulent flow over a flat plate. In reality, if you're looking at a motorbike in the back of the helmet and you get a detachment of flow and a reversal of flow, that wall function just makes no sense. So wall functions really only are good estimates if most of your flow is attached and similar to the conditions which wall functions were designed. The alternative then is you have to resolve the boundary layer. If you resolve the boundary layer, then you don't have to worry about like detachment or conditions that do not follow the law of the wall. So you can see there's a lot more rules of thumb here than maybe some of the things we looked at before. So this is once again turbulence models or approximations, so you have to be very careful when you're using it. Okay, I just have last couple of slides on just some other types of boundary conditions, and then I'm going to talk about the terminal. Okay, inlets, outlets. And this is focusing on incompressible flow, low Mach number incompressible flow. So if you go to design rockets, you might have to follow different kind of principles where you have compressible flow, high Mach numbers. But for low Mach number flows, generally at an inlet, you will specify a value. You will say you know the value of whatever you're solving for, temperature, velocity. The physical argument here is if you have fluid coming into a domain, then it's coming from the inlet. So we have to know what's coming in. Like that's not part of the problem. You just have to say, if fluid is coming in at a certain temperature, the boundary condition needs to say what the temperature of the fluid is. You can't have any other condition because then you won't be able to solve the problem. So generally for almost all conditions, you need to specify the value of the inlet. Mostly, there are exceptions that you might do something else. One exception is the pressure. So when we have an incompressible fluid, which is an idealization, then the density is assumed constant. So that means pressure waves travel at the speed of sound. So every piece of fluid can't be compressed. So that means the speed of sound is actually infinite in an incompressible fluid. So when it's solving for the pressure fluid, essentially it's not infinite, but it's like numerically very high. As it's iterating, the solution procedure iterating, there will be very fast pressure waves propagating around. And they can obviously travel much faster than the speed of the flow coming in. So to provide physical conditions for pressure, you can't specify the value of pressure normally. There are some scenarios you can, but you can only specify a gradient condition, and that allows artificial pressure waves to travel out of the domain so the procedure can solve. So that's the only exception. At an outlet, we normally specify the traction or the force. So this might be the definition of traction from Newton's law. It might have some function of the gradient velocity and some pressure condition. But typically we assume that a certain gradient of velocity is 0, and that means these terms go to 0. So essentially this means the traction on the fluid outlet is just the pressure. It's just a normal force pressure. So normally we'll specify the gradient of velocity to be 0, and we specify a known value of pressure on the outlet. That's the normal setup. One other thing, which is a choice even for your assignment, the inlet flow, when you have a turbulent, like a RANS or LES simulation, you have to specify how much turbulence is in the incoming. So if you're solving for K epsilon, you have to say what K and epsilon are incoming, because the simulation doesn't know. Like it could be very turbulent fluid coming into the domain or not very turbulent. So as one way to do that is you can specify what's known as the turbulent intensity. This is the percentage of the overall energy of the fluid which is stored in the kinetic energy of the turbulence. So if you're a car just driving along in normal weather, it'll typically be less than 1% of the energy of the kinetic energy of the air would be these turbulence. So 1% is already starting to become medium level. If you have forced internal flows, a lot of turbulence, then it becomes 1.5%. And if you have like fans or something like that, it can go as high as 20%. So just to give you a rule of thumb. So if you set that value very wrong, the predictions could be very difficult, and could be quite different. So if your inlet boundary, say if it's a car is far enough away, if you set it slightly wrong, it will kind of stabilize and it will kind of reach an equilibrium that if you double or half the incoming A, for example, or turbulent intensity, it won't affect the prediction here. But there are cases where you do need to be careful of how you set that value. So if you know the turbulent intensity, you can only convert that to a K value and an epsilon value, or in Fluid, you can just specify the turbulent intensity normally directly. And the last boundary condition I just want to talk about is kind of free or entrainment boundaries. These are broadly boundaries that could have flow coming in, but it could be out at times. So far we've kind of split it into only inlets where flow comes in, outlets where flow goes out, and walls where flow doesn't go through, whether it's slip or no slip. But there are situations where you might have a boundary where sometimes or some parts of it flow might be going out, some parts of the flow might be coming in. So you can call those free boundaries or entrainment boundaries. And there's different ways to set those up depending on your particular application, and it can affect the prediction. And a general rule of thumb is if you have a boundary like this and you're not sure what to do, just make your domain bigger, move that away. And then it doesn't really matter what condition you set because it shouldn't affect what's happening, like your car or something like that. But there are choices of boundaries that maybe are more physically available. Here's an example. This is from this open goal book. There's an inlet here, an outlet there, and there's walls, and the top is this free boundary. So physically what might happen is the flow comes in, goes out here, but some of the fluid will be turned here and be driven out here, like an outlet there, and it'll kind of cause a recirculation, so it might come back in here and go out here. So we need to specify boundary conditions for velocity and pressure. So if we specify just an outlet condition on the top, the normal way to do that, if you set it up and run that simulation, it'll be unstable, it just won't converge. And what will happen is if you look at the intermediate unconverged velocity fields, they'll flip between fluid, lots of fluid going out and then fluid coming back in and in and out, and it's kind of physically unstable. So if you set that all to an outlet, it won't be stable. But there are special conditions, so you can specify a total pressure condition, and total pressure includes this dynamic pressure, this velocity term. So basically, whenever it's an outlet, wherever the fluid wants to go out, when it wants to come back in, you adjust the pressure not to be 0 or some reference value, but to be a function of the velocity. And then you can get stable, reasonable simulations. So this is somewhat, seems like an ad hoc or an arbitrary example, but I'm just trying to highlight that if you have conditions like this, you just need to be careful of how you set them up. There is in OpenFOAM and Fluid something called inlet-outlet, and the most basic setup is you have an outlet, and then if the fluid tries to change direction, it will just switch to a wall. So if fluid's going out, that's fine, it's fully an outlet, and then if any face of the mesh starts to come back, it just turns into a wall, so it doesn't let anything back. So that's, I think they're called inlet outlets. So just so you know, that's what happens. So if that's not representative of what happens in your case, you might get strange pressures at the outlet where suddenly the wall appears, or it might be unstable if walls appear and disappear, etc. Okay, and then symmetry planes are just like before when we talked about stress analysis, and there's thermal conditions we're not going to talk about. Free stream, if you go to look at aerofoils, or planes or something like that, or even for cars, the atmospheric far away conditions are often like in Fluid has specially designed boundary conditions for that kind of minimize the effect of the domain size, and they kind of call them free stream conditions. But all of these are based on some in some way derived from a fixed value or a fixed gradient, so a Dirichlet condition or a Neumann condition. Yay. So for the remainder of the day, I'm going to talk about the terminal. So I'm going to switch gears. Oh, oh. Okay, so I'm going to change to kind of something different, and hopefully this will be more hands-on. Maybe I'll do some hands-on now, or I might leave it mostly for the next lecture. So I'm going to talk about the Linux and Unix terminal. So for the last phase of the module is you're going to learn about this OpenFOAM software. OpenFOAM is an open source, mostly a CP software. You can do stress analysis in it, but it's mostly a CP software. So it's OpenFOAM, but it's primarily developed in Linux, and you normally use a Linux terminal too. So this is why I'm teaching you about this. So you might say, oh, that seems a bit bizarre or archaic, but there's a few reasons why it's good to learn a Linux terminal. So one, the last lecture we'll get to is high performance computing. The last lab is high performance computing. So you use one of these supercomputers. So all supercomputers, most of them are based on Linux now. So even to run Abacus and ANSYS on the UCD supercomputers, you have to use a Linux terminal. So you have to run through Linux. So Abacus, ANSYS, all the commercial softwares are typically released for Windows and Linux, normally not Mac. But OpenFOAM is just primarily Linux. So it's at least I think it's a useful skill set to just learn the Linux terminal. So maybe just for the next 5 minutes, I'll talk about what it is, and then I might need the hands-on to answer. So what is a Linux or Unix terminal? So it's sometimes called a command line interface or a CLI. And essentially, it's just a text interface for interacting with the computer, interacting with the operating system. So mostly, you guys, I guess, are using a graphics-based system. So in Windows, if you want to copy a file, you open up a graphic interface, you click on it, you right-click copy, or you drag and drop, and things like this. So you can do all those things in a terminal. It might be more difficult to do it, or it might be easier depending on the task. So this is an alternative approach called command line. So you can directly interact with the operating system, giving it commands. So you type in a command, press enter, it executes that command, and there might be some output from that. And the alternative to a CLI command line interface is a GUI or a graphic user interface, which is what you're more familiar with. So text-based interface. The idea when you'll see when we're using OpenFOAM to run the jobs and set up boundary conditions is all through this interface. Some phrases to be aware of. So there's something called a shell. So when you type a command, there's a program running, processing the commands you type. So you type a command, press enter. There's a program called a shell, which looks at that command and does something based on whatever you do. So there's various shell softwares. So the one that's by default in most Linux setups is called Bash. And you'll see a lot of names that come from computer science people, so they're all these super cool names. But the Bash is the born again shell. So there was a shell before this, and someone made a born again shell. So that's all Bash. So Bash is now the default. Yeah, on Mac, Z shell is actually the derivative or the main one, and then there's T shell as well. They're all very, very similar. It's just maybe how they interpret a particular command, they have a different syntax, but they're very, very similar. So there's lots of things you can do, like file management system with admin, installation, etc. And we're going to go through some of the basic commands you need to run OpenFOAM. So let me see. Yeah, I think I just give a high level overview, and then I'll maybe leave it till Wednesday to go through all the details of actually hands-on how to use these. But just at a high level, for example, if you want to type ls, that will show all the files in the current directory you're in the terminal. If you want a cd, that's change directory, that's how you move into another directory. You could move into another directory, type ls and see what's inside it. But then there's lots of other commands like rm is to remove a file or directory, cp is to copy, mv is to move. You might think that, oh, I have to learn all these new commands, but actually with 10 commands, it's probably enough to run OpenFOAM. You don't need that many. You just need to be able to open file, delete a file, copy a file, and move around. That's about it. Then, if you want to edit a file, you normally use a text editor. So you could use Notepad in Windows, but the most popular ones are VI or VIM, it's called Vim and Emacs. They're kind of old school computer science people use Vim or Emacs, and you'll find Lots of memes online in the computer science world of why one's better than the other one, and now as well. And then there's other things to do with permissions, which are a little bit different. So all the points I'm hitting on here, I'm going to show you hands-on practical examples of how to use these on the first lab for OpenFOAM is essentially how to demonstrate some of these things. And you'll see on the exam as well, I will have some questions that show commands and you have to explain what they are, or you have to say what commands you need to run to do so. A couple of ones to point out: remote access. So through the terminal, you can use this SSH command or other commands to log on to other computers on the network. That's how you log into these supercomputers. You just do it through a terminal. Or for example, I could log on to a workstation in my office from here, and that's how you can run jobs or access. But also there's things that you'll see that are very easy to do in a command line interface that wouldn't be in a graphic interface. So if I have a folder of 1,000 photos and I want to find ones with certain strings in their name or certain patterns in their name, I could write a little command or script to automatically rename all of those or add _Philip to the end of every photo. So I can do that with one command, whereas with a graphic interface, that would be a pain. That's to rename it. So there are some things that are just more efficient in CLI, and there's some things that are just way more efficient in a graphic interface. And so courses for courses. So why you should learn this? I've already kind of said about this, but some specialized software, such as OpenFOAM, you must use the terminal. That's one reason, and that's a practical reason why we're doing it. But remote system management and logging onto high performance computers, that's another good reason to do it. And so that's much easier, often through a terminal and using a graphic interface. And terminals often need very low internet bandwidth, so you can log in and you don't need much internet traffic to control things. If you have to get a remote desktop, you need a good internet connection to do that. Scripting and automation, you can automate jobs, you can do a parametric study, you can make a script that you run multiple models, multiple ways, and that's maybe straightforward to do. There's certain tasks, like I said, that are more efficient and easier to do in a terminal, and some ones that are not. And debugging and troubleshooting, sometimes like if an Abacus job crashes on a supercomputer, you have to go through all the text files that the graphic interface doesn't give you access to, for example. So it can be useful just to be able to, you don't have to use a CLI to do that, but that's another way. Let me see. One last slide then, I think. So to give you just a bit of the background. So Unix came out of Bell Labs, like lots of things in the late 60s, and was designed as essentially a multi-user operating system that either computer that multiple users can use at the same time, logged in from different terminals. That's the idea. Then in the 80s, this Linux project started, and basically Linux came along and just thought Unix is cool, but you kind of had to purchase most Unix things, so they just wanted to make a free version of it. So most Unix wasn't free. So there's a few guys, famous people that in the Linux community that came along and established Linux as basically a copy of Unix. So they made something called GNU. And once again, computer scientists, so GNU stands for, the G stands for GNU, and the N is not Unix. So it's a recursive acronym. So the G doesn't stand for anything, it just stands for GNU. So it's GNU, not Linux, GNU, not Linux, GNU. Anyway, so this just is this open source project. So Linux now is a family of open source Unix-like operating systems. They're not technically Unix, but they follow the same terminal structure. And Unix is a family of other operating systems derived from the original Bell Labs. So Mac is actually a Unix. So it has a Unix terminal, a true Unix terminal, and Linux is very similar. So you can find this off Wikipedia. So this is Linux here, this original one. So the GNU project started in the 80s, and there's loads of Linux operating systems. We're going to use Ubuntu. But you can find Darwin is Mac, so this Darwin kernel is what Mac is built on. But there's other free versions of Unix and commercial versions of Unix now. But all Linuxes, or most Linuxes, are free. Though some of them are commercial. So there are just loads of these families of operating systems that are all very similar, that are essentially not Windows. All right, I will stop there now, and then we can do the hands-on stuff next week. Thanks so much.